Hey guys, and welcome to this video on graphing functions. So let's make it happen. Alright, recall before when we used to solve equations such as the 4 in front of us. And why don't you take a second to pause the video and actually solve them. And recall, to solve an equation means to find the value of the unknown variable that, when substituted into the equation, makes the equation true. Now note that each of these equations has exactly one variable, namely x. And also, each of these equations has exactly one solution. Now we're going to be dealing with equations having two variables in it, such as y equals 2x plus 1. Now notice how similar this equation with two variables is to the four equations we had above. Instead of negative 5 equals 2x plus 1, or 7 equals 2x plus 1, or 3 equals 2x plus 1, or negative 1 equals 2x plus 1, we now have y equals 2x plus 1. So it's clear as the variable y takes on different values, the variable x is going to have to take on different values as well to keep the equation true. Or what we'll see more frequently is as the variable x takes on different values, the variable y is going to have to take on different values too to make the equation true. Now, we have two ways to think about these equations when we see that they have two variables. The first way to think about them is to think of them as, well, equations, for which we are trying to find solutions. Solutions are not single numbers anymore. In this case, a solution to an equation with two variables in it is an ordered pair of values for the unknown variables, such that when both are substituted for their respective variables in the equation is true. The other way to think about it is to think of it as a rule, where y is the output and x is the input. In that case, we're looking for all input-output pairs to our rule that make the equation true. This rule may or may not be a function. But whether or not you consider y equals 2x plus 1 an equation, or y equals 2x plus 1 a rule or function, either way, we're still looking for ordered pairs, and we're going to try to find all the ordered pairs that work for y equals 2x plus 1. So if we want to talk about solutions to this equation right here, we're going to have to give both x and y pairs that'll make it true. So for instance, if x were to equal negative 3 and y were to equal negative 5, I claim that that statement would be made true. Or, if x equaled 3 and y equaled 7, I also claim that that statement would be made true. We could also represent solutions to that equation in ordered pairs. Remember that in an ordered pair, the first entry represents the input or the independent variable, and the second entry represents the output or the dependent variable. Of course, in this case, the convention is that x is our independent variable and y is our dependent variable, so we don't need to tell the reader explicitly which entry goes with which variable because it's understood. If x were 1 and y were 3, that statement would be made true. Or if x were negative 1 and y were negative 1, the statement would be made true. Of course, we could have expressed our first two xy pairs, which were solutions to that equation, as ordered pairs as well. And note that these four solutions to this equation with two variables coincide with the four equations that we solved at the very beginning of this video. So here we have four solutions to this equation. What I urge you to do is pause the video and try and find some more xy pairs that'll make that statement true. Here are four more ordered pairs that I found. Maybe they're the same as the ones you did, maybe not. But question, how many pairs of numbers do you think we could find that would make this equation true? The answer is infinitely many. We could go on and on and on forever and ever and ever, finding all the ordered pairs that make this equation true. I mean, we could spend our entire lives finding those pairs of numbers, and we'd never finish. We'd never even be close to finishing. So instead of spending our entire lives listing out these pair of numbers, let's try to capture all of them in a different way. Note, since there are infinitely many pairs of numbers that will make the equation true, the easiest way to capture them all may be to create a graph. So let's pull up a set of axes, graph the ordered pairs we have, and see if we notice anything. Alright, here's our graph, here's our equation, here are the ordered pairs that I found, maybe you found some more, but before we graph them, remember we always want to label our axes on our graph, even if it's by the standard convention that the horizontal axis is our independent variable x, and the vertical axis is our dependent variable y. Alright, now let's go ahead and graph these ordered pairs. Interesting, when we graph all these ordered pairs, all the points seem to create a line. But what does that mean for our ordered pairs when we graph them to make a pattern? In this case, a line. Well, since almost always when we're working with an equation with two variables, we're going to have infinitely many ordered pairs, we couldn't ever hope to list them all or graph them all. So our general strategy now is use the equation to find as many ordered pairs as we can and then graph them. And if they create a pattern, we can confidently say that that pattern is going to continue on forever and ever. And we can extrapolate and create a graph. And what's so great about that graph is that it will capture every single input-output pair or every single ordered pair solution to that equation, all the ones with fractions and decimals, in one nice succinct picture instead of spending our whole lives listing them. Let's go ahead and actually connect them and draw this line. Alright, now if this line represents all the solutions to our equation y equals 2x plus 1, it means that any point on this line, if we were to substitute its x coordinate in for x and its y coordinate in for y, should make that statement true. So let's pick a point at random and see if it works. How about the point -2, -3? Let's see if that'll work. Whoa! Awesome, that point definitely works. Alright, let's try one more just to make sure. How about the ordered pair -4, -7? Will that work when we plug its coordinates into the equation? Alright, that one worked too. And in fact, for any point on this graph, even if the coordinate has a fraction or decimals in it, if the x and y coordinates of that point are put into the equation that was graphed, y equals 2x plus 1, they will make the equation true. And that's why this graph is such a great way to represent all of the infinitely many pairs of numbers that'll make this equation true, whether they're nice easy ones with integers like the ones that we can see and the ones that we've listed, or if they're weird ones with fractions or decimals or square roots or who knows what, they are all captured by this graph. And I'd like to explore this a little bit more using a graphing calculator on the iPad. Alright, so here's the graph of our equation, y equals 2x plus 1. It's a line, just like the one we just drew, and here's some of the ordered pairs that we talked about before. Note that all of these have integer coordinates, but there's no reason we couldn't have inputs or outputs that were decimals. For instance, I could make the x coordinate 2.38, and we get a y coordinate of 5.76. Or we can make the input 0.725, and we get an output of 2.45. And if I drag my finger along this line, you see that there are all sorts of decimal input and output pairs that are possible. In fact, infinitely many of them. And so that's why this graph is the best way to capture every single solution to this equation, or every single input-output pair to this rule. Alright, back to our hand-drawn graph for a moment. Note that because of our graph, all we can see are inputs from -10 to +10 and outputs from -10 to +10, but there are so many more inputs and outputs that are going to work for this equation, and that's why we place arrows on either side of our graph, in this case a line, to show that this trend is going to continue on and on forever and ever. One more reason why this graph captures all of the infinitely many solutions to this equation, or input-output pairs, for this rule. Two very important points, and we're going to start by defining them. The y-intercept of a graph is where the graph intersects the y-axis. One thing that's really important is the x-coordinate at the y-intercept will always be 0. Now here it is, right here on our graph, but it's really helpful to also confirm our y-intercept algebraically. And all we do is we take our equation and we just substitute 0 in for x. So in this case, we'd say that the y-intercept is the point 0, 1, or you can just give the y-coordinate and say the y-intercept is 1, since of course the x-coordinate has to be 0 there. Our next definition is the x-intercept, and the x-intercept of a graph is the point, or the points, where the graph intersects the x-axis. Of course, the y-coordinate at the x-intercept, or x-intercepts, will always be 0. So here it is right here on our graph, and it appears to be somewhere between 0 and -1, maybe -0.5, but let's also confirm algebraically by just substituting 0 in for our y-coordinate in our equation and solving for x. So in this case, we'd say that the x-intercept is the point -1/2, 0, or you can just give the x-coordinate and say the x-intercept is -1/2. Alright, let's try another one. Let's please graph all the ordered pairs for the following equation or rule. 2y plus 4x plus 6 equals 0. Now our first strategy to find solutions or ordered pairs is to just substitute random numbers either for x or for y or for whatever the variables may be, and use the equation to then solve for the other. So either substitute something in for x and then solve for y, and then you have an ordered pair, or substitute something for y and then solve for x to find an ordered pair. Let's try substituting in x equals 2, and then let's try substituting in y equals 5, and let's see what ordered pairs we get. Whew! Alright, so we got the ordered pairs 2, -7 and -4, 5. I went ahead and graphed those on our axes, making sure to label our axes as well. And you know, that was a whole lot of work just to get 2 ordered pairs. I mean, this just seems like a pretty tedious way of going about finding ordered pairs. Now the question is, why was our last equation, y equals 2x plus 1, so easy to find ordered pairs for, and this one's so difficult? Well, when we had our equation in y equals form, all we had to do was just cycle through x values, and it was so easy to compute the corresponding y values. And this brings us to our second strategy, which is to put our equation in the form y equals equation, or output equals equation, then substitute values in for our independent variable, oftentimes x, to find ordered pairs. So let's go ahead and take this equation, 2y plus 4x plus 6 equals 0, and transform it into a y equals equation. Now that we have our equation in y equals form, it's going to be easy to cycle through values of x and find their corresponding y values much more quickly and efficiently. Now, we might as well be systematic when we substitute in our x values. I prefer to start with the x value 0. It's often going to be the easiest. Then I try some positive x values and some negative x values, plot those points, and see what the graph looks like. Now, there's no guarantee of how many input-output pairs you need to find before you know what the graph looks like, but of course, the more ordered pairs you find, the more likely you are to have an accurate vision of what this graph is going to look like. So why don't you pause the video and try finding some input-output pairs for positive inputs, some input-output pairs for negative inputs, and I'm going to do the same, and then let's reconvene and see what we got. Note, I've only found 4 more input-output pairs, just using positive inputs, but I'm already almost out of space. What's really nice is that when you have a simpler equation in y equals form, like this one, you may often be able to get away with doing some of these calculations in your head. Now, of course, we want to make sure to do so diligently and not make any mistakes, but isn't it nice to have a simpler equation that we could work with in our head? So I'm going to go ahead and just draw a table of values and insert some more input-output pairs. Again, we see that our input-output pairs are creating a line on our graph. So let's go ahead and connect them and extend that line. And remember, there are far more input-output pairs that extend far beyond this set of axes. So let's make sure to put some arrows on our line. Awesome. Now let's just talk about our intercepts. Our y-intercept appears to be the point 0, negative 3, which we can confirm algebraically and probably mentally just by substituting in a 0 for x. Of course the y value would be negative 3. Our x-intercept isn't going to be so easy to eyeball. It's somewhere between negative 1 and negative 2, so let's use this equation to find the x-intercept by substituting in 0 for y and finding the x-coordinate. And so we find that the x-intercept is negative 3 halves, which our graph confirms.